All right, in today's lesson, we're going to be looking at graphing exponential functions. So starting us off here, I've got two graphs. First graph is of y equals 2 to the x. The next graph here is y equals 1/2 to the x. And what we're looking at is the difference between these. These are the two main forms of your exponential function. Either you're looking at something along the lines of an exponential growth, or something that looks like exponential, or we have something called an exponential decay. All right, under what conditions do we have a graph that has this general form to it? First of all, your exponential is of the form a to the x. And if that a value, known as the base, is greater than 1, and then you have what's called an exponential growth function. Exponential growth functions have this general form to them, where they start off getting infinitely close to our x-axis, never touching the x-axis, and getting larger and larger and larger and larger as x itself tends towards infinity. What separates itself from your, let's say, linear function is that every successive step in your exponential function becomes considerably larger in size. So for instance, when x is -4, the height is illustrated by this blue line. Taking a step of 2 units to the right, you can see that that jump becomes much more significant. Taking a jump 2 steps to the right again, we can see that even though we're taking equal steps away, each successive output becomes much and much larger. So because of that, we call that exponential growth. And similarly, we have the idea of exponential decay. And exponential decay occurs when your exponential function, so in this case y equals a to the x, is such that that a value, that base, is between 0 and 1, again, not including 0 or 1. When you have that, you have a function that is decreasing each successive step to the right, but is decreasing by larger and larger amounts each time. So it's falling faster and faster and faster towards my x-axis. And we can see this graphically as well. You'll notice here I start off at 0, and I am, this far away from my x-axis. Taking a step 2 units to the right, I'm now considerably closer, and another step 2 units to the right, closer still, and you can see even closer still at the 6. So again, what's happening here is when you look at these exponential functions, in this case here with the exponential decay, you are falling faster and faster and faster towards your x-axis. Again, never hitting your x-axis, but getting infinitely close to your x-axis. And again, back just to remind you, with exponential growth, you're infinitely close to the x-axis, and as x gets larger and larger and larger, you are growing faster and faster and faster away from that x-axis. Let's now compare your exponential growth function with our power functions. As discussed earlier, we can see that any exponential growth function will eventually grow faster than any power function. So initially, it might be the case that your power function might lie above your exponential function, but at some point, the exponential function, that is the speed at which the exponential function is growing, will eventually grow faster than your power function and lie above it. So we can see that here in this graph here. You'll notice here I'm comparing y equals x to the power 4 and y equals 2x. As we just talked about, that's a growth function, y equals 2x. And you can see here on the initial starting, your x to the power 4 is actually growing faster and faster and faster until we hit this point right here. At this point, you can see your exponential growth function now takes over and is now growing at a faster and faster and faster rate. So eventually, in this example here, your exponential function will take over. And just to illustrate the fact that this is actually the case, if you take a look at an exponential function, so let's say y equals 1.005 to the power of x, again, this is greater than 1 for a base, so this still falls under the category of a growth exponential function. And you can see here, if I compare even that to x to the power 4, one of our power functions, eventually your exponential growth function will take over. Now this happens somewhere between 5,000 and 10,000 units for your x value, but again, eventually the exponential growth function will take over and will grow faster and faster and faster away from the x-axis. The same thing can be said about your decay functions. If you're comparing your exponential decay functions, they will approach the horizontal axis faster than your power functions. Again, to illustrate this idea, compare here y equals x to the negative 2 versus y equals 1 half x. Again, y equals 1 half x is an exponential decay function, and you can see here that this is clearly decreasing at a faster and faster rate compared to our y equals x to the negative 2 function. While the differences between these two graphs may not look that drastic in this example here, if we take a look at this idea of the decay function further along, now we can see here your decay function in this example is decreasing faster. Even at 20, we can see it's decreasing much, much quicker towards your x-axis, your exponential decay function. But as you zoom this out and take a farther look away, as we approach, let's say, x is 100, you can see the difference is quite drastic between these two. As my x value gets larger and larger and larger, the difference between x to the negative 2 and y equals 1 half x is larger and larger and larger difference. So we can see here that, again, the fall gets faster and faster and faster. So the gap between these two functions becomes larger and larger and larger as x gets itself larger and larger. All right, I thought we'd take a look now at graphing some exponential functions. So the first one we're looking at here, is I want to graph y equals 2 to the power of absolute value of x. So what we have here is this is what it looks like. This is our graph of y equals 2 to the absolute value of x. Let's take a look at how we discover that to be the case. If you look at your graph of your exponential growth function, so forget the blue here. Let's actually white out that blue at first. And what we have here is we have our normal y equals 2 to the x function, our normal growth function like we've been talking about. What happens is your y equals 2 to the absolute value of x, what's it going to look like? Well, it's going to output two different values. It's either going to output a 2x or a 2 to the negative x, depending on the value of x. So in this case here, if x is greater than or equal to 0, your absolute value can just drop, and it'll just be your normal growth function. That's why you see here that what I have here in blue, this represents x being greater than or equal to 0, and that is exactly the same graph we have for our y equals 2 to the absolute value of x function. They're exactly the same. There's no change. Now, on the other hand, when x is less than 0, the absolute value of x becomes negative x. And now this is where the graph looks different. Now, when x is less than 0, what happens is if I were to input a value of negative 1, normally it would output this value. If I would let x be negative 2, it would output this value, negative 4, output this value, and you have this decreasing sort of fashion as I read this from right to left. But now if I take an x value of minus 1, you're going to multiply that by a negative sign, as you see here. So it's going to act as if, just as it did when x was positive 1. So we're going to end up getting an output value here instead of here. Using a similar logic, when x is negative 2, normally your growth function would be here. But it will act just as it did when it was at positive 2, because again, when I let x act on this value here, when x is negative 2, it's going to be negative negative 2, making it positive. It'll output just as it did at 2, so that value will be all the way over here. And then that's where we got our blue line that you saw. So y equals 2 to the absolute value of x will have this shape to it. Let's take a look at another graph. All right, so you want to go ahead and graph the following function here. This is y equals 2 to the power of negative absolute value of x. So let's first take a look at what does this function look like in a piecewise function. Well, when x is greater than or equal to 0, we're going to drop that absolute value, and your function just becomes y equals 2 to the negative x. And when x is less than 0, we can also drop that absolute value, but that will cost us a minus sign. Those two minuses become positive, and now we have y equals 2 to the x. So writing this a little bit differently, what does this mean? This means that we really have 1/2 to the power of x when x is greater than or equal to 0, i.e. when x is greater than or equal to 0, our function is your exponential decay function, and otherwise it's your exponential growth function when x is less than 0. So what I did here was I went ahead and graphed your 2 to the negative x, also known as 1/2 to the x, your decay function, and then your growth function on the same Cartesian plane. And you'll see here in red we have our decay function, and in green we have our growth function. So what's going on here graphically in terms of this function here? Well, when x is greater than or equal to 0, it's the decay function. So when x is greater than or equal to 0, we're going to take on our decay function. So our new function will look like this. And then when x is less than 0, we take on our growth function looking like this. So what we have highlighted here in purple represents y equals 2 to the negative x. Let's just erase these other graphs and take a look at what we have. So going ahead and erasing
and that concludes
what we have and just kind of leaving what our graph of y equals 2 to the negative absolute value of x is going to look like. And it'll look like as follows here.